Hello everybody, today we're going to be presenting to you FarmNG Amiga Robotics Challenge.
Hello, everybody. My name is Osmar Alvarez, and I'm a student at Heritage University in Toppenish, Washington, currently studying computer science. And the little fun fact about me is I spent my whole life in Toppenish, being born and raised here. And with Toppenish being a major agricultural town for many different fruits, I've helped my parents throughout my life with their work, such as picking apples and moving apple bins, which I think helps me immensely in this internship that I'm working on.
And with that, my name is Robert Barragan. I am also studying computer science at Heritage University, and today I'm going to be describing 3 fun facts about me. So, one fun fact about me is I grew up in Yakima, Washington. Another fun fact about me is that my parents owned a bakery and they sold bread, which is shown in figure 2. And the last figure is basically my parents' business was on a newspaper.
So our problem that we're hoping to fix with this internship is that bin management requires significant manual labor and workers handle and place bins to optimize collection. So our mission for this project is to automate and streamline the collection of apple bins, while the overall vision that we hope to achieve with this project is the increase in collection speed and distribution speed of fruits to local stores and vendors. We also value the preservation of the environment and of workers, so we aim to replace big gas-consuming tractors and allow workers to rest instead of having to haul away apple bins after they're finished picking.
And with that, we're going to go over our project overview, which is to build a system capable of identifying a filled bin, navigating around empty bins, and efficiently transporting the filled bin to a designated handling area. And the way we're going to do that is with the FarmNG Amiga robot, which is shown in figure 1. So basically, here's all the different hardware we're going to be using in the entire internship. So our first hardware is the camera, which is the Oak DWPOE, which has RGB data, and it also has AMRS localization and 3D mapping. For our LiDAR sensor, we have the SICK LMS1XX, which has a range of 20 meters, and also AMRS localization and 3D mapping, which is important for our simulation. Our next hardware we're going to use is the FarmNG Amiga robot, which has an 1,000 pounds capacity and an 8-hour runtime. And lastly, we have our linear actuator, which has a force of 220 pounds to 450 pounds. And it's also compatible with ROS, which is a robotics operating system that allows us to use multiple packages to use all these different hardwares together. So the ROS2 packages we're going to be using throughout the project are Nav2, which is a navigation framework that provides perception, control, localization, visualization to build high reliable autonomous systems. We're also going to be using Arvis2, which provides a graphical interface for users to view their robot, sensor data, maps, and more. And lastly, we're going to be using Gazebo, which allows us to test and experiment robots with realistic physical scenarios.
So for our process, we start off with the design of the robot and its auxiliary parts. So we decided to go with the forklift mechanism, and to create this, we use CAD files, which simply stands for computer-aided design files. And that works with the linear actuator that we have that will lift up the bins. This is shown in figure 2. And in order to create a functioning robot, we also need to simulate it. And to do that, we need to create a URDF file, which stands for Unified Robotics Description Format file, which basically acts as a blueprint for the robot. And in order to use our robot, we also need a navigation software. This is able to take in data gathered from the LiDAR system and create a map that tells the robot the best course of action that it should take.
And with that, we're going to go over our scope of work, which is a 3-step process. The first step is to get STL designs. The second step is to create an orchard and Amiga URDF. And third step is to set up sensors and create maps.
So for us to create our parts and the robot, we need to create STL files, which stands for stereolithography files. It's basically a 3D printing file format, and it's made up of many triangles that describe the surface of an object. In these first two pictures, we have STL files made by our mentors that were made quickly for us to be able to insert them in our simulation and then have practice with our simulation. On the right, we have an example of an old lifting mechanism that we no longer use. And on the next slide, we have updated pictures of our STL files. So this is our files for the Amiga robot. On the left, it's the Amiga wheel and base. On the right is just the base with the bars. And it is important that we have proper measurements and readings in order to have our test simulations provide proper data.
And just like Osmar said, the two STL files, we compiled them and created a URDF file in Arviz2, which is shown in Figure 9. And in Figure 10, our mentors have created an orchard URDF in Gazebo, which we're going to be using it in our simulation. And Figure 11 shows the simulation in action with the Amiga as well as the orchard. So in the simulation, as you can see, there's blue, which are the LiDAR sensors being displayed in the orchard simulation, as well as the camera, which is that little box in the middle that shows how the orchard is being viewed through the robot. And with that, it's also collecting data, which is shown in Figure 12. Based on its initial point, where it's at right now, it's able to create a cost map within the orchard world. Knowing this, we also faced a lot of challenges and solutions. So our first challenge was hard coding models with URDF. So this was our main issue at the beginning because we had to create objects. So for example, boxes and circles for the wheels, which was very redundant and took too much time. So our solution was to download Blender and import the STL files we created on Onshape and use those to create base and collision meshes. For our second challenge, we had ROS1 package limited features. So in ROS1, we had a lot of packages that were outdated. So our solution was to download ROS2, which provided access to new packages that were not in ROS1, like nav2.
Another challenge that we faced was obtaining accurate CAD files. So for us to properly test the robot, we need to have accurate CAD files of the Amiga robot. And while we had some files that our mentors made, they weren't exactly accurate. So our solution to this was to contact the developers of the Amiga robot, so they would be able to provide us with some more accurate and detailed files, which they happily did.
And with that, we want to thank our team, Syed, Priyanka, Dr. Karki, Safal, Achu Padel, Dawood, Paul, Bethany, Michaela, and Salvador. And with that, we want to thank you all for listening to our presentation. Are there any questions?